programming. And this was the last time, the last picture that I showed you. Am I recording? Let me, yeah. This was the last time. I think for the other section, maybe I should come from the beginning a little bit. I showed you this hierarchy. Actually, the book has a similar hierarchy. We said that let's have a class named shape, and this class is a very simple class, and it has only maybe three functions that are not implementable, and this is the implementation of the whole class. Actually, it is not much. So I have a constructor which will not do anything, and I have the draw and the area, right? No. Let me show you this one. Let me show you this one. Yes, this is the shape.h. In shape.h, I have the constructor which doesn't do anything, and I have the area function, perimeter function, and the draw function. They are all pure virtual functions. What do I mean by pure virtual? Pure virtual means that it is virtual. That means that if I call it in a certain way, its meaning will be decided during the runtime, right? That was the meaning of the polymorphism. Its meaning will be decided during the runtime, and I am not going to provide any implementation for this class. That's what I meant, okay? And I have a global function that takes a vector of shape pointers, and it returns the total area of the shapes contained within this vector, okay? That's what I am going to do. So this is shape.h, and shape.cpp is very simple. I just include shape.h. Since I don't have anything to implement, constructor is empty. It doesn't do anything because I don't have any data members in it. And in my constructor, in my global function, I do this. I say I have a double temporary, and in a loop shape pointer that iterates over this vector v. Okay, I do this p arrow area. So this was the whole thing. I mean, this line is the reason why we are studying this chapter number 15. Is it 15? Chapter number 15. I guess it's chapter number 15, polymorphism chapter, right? That's the whole reason why we are studying is because this call is a polymorphic call. I cannot know what this line means until I hit the runtime. During the compile time, I cannot know what this is. Okay, I cannot, because the area might mean the area. Well, first of all, I know that the area cannot be this because there is no function implemented for this one. So area must be something that should come from any derived class from this shape, but I did not derive any classes yet. So how does the compiler produce code for this one? Remember this one? I said that maybe I can let's say these are not pure virtual functions, but just simple virtual functions. Let me make them simple virtual functions. Okay, let me make them simple virtual functions, not pure virtual, but simple virtual. I will change them later. Okay. They don't do anything, right? They don't do anything. They just, maybe they should return something, but I am not going to write them. So this is now possible. I make three objects of shape, and I put them into this vector, shape pointer vector, by taking their addresses, and call this one total area. Okay. This code compiles and links, and it even runs. Okay. It returns something stupid, but it even runs. But I know that the meaning of this area might change from run to run. Why? Because later I might derive a circle class from the shape class, or a rectangle class from the shape class, or any other shape class from the shape class. Okay, and I may implement all of these functions in a meaningful way, and I can write another driver like this one. I include shape.h, circle.h, and I make circles like this one. I can do shapes and circles, and I call the total area. I did not recompile total area. Total area was compiled before, okay? Because total area was compiled inside this shape.cpp. All I do is to compile the circle CPP, driver to CPP, and link them together with shape.o. Inside shape.o, this code was compiled long time ago, before I had written this circle.cpp, and everything works. How does it happen? It happens because I told the compiler that these three functions are virtual functions, okay? They might be used polymorphically. They might be bound dynamically later during the runtime. If I call them in this format using a pointer to the base class, or using a reference to the base class. In this case, I am using a pointer to the base class. Okay, so the meaning of this line will be different from run to run, from this function call to call, or even at every iteration of this for loop. Okay, the meaning of this line will be different. That's why we say that. Polymorphism is associating many meanings to one function. Okay, that function doesn't mean just a single thing. During the compile time, I may not know what that function means. Okay, I will know it when I come to the runtime, when I execute this line, okay, when I execute this line, I get this pointer from this vector, and I follow the pointer. I found the object, and I ask the object, where is your area function? That object tells me the area function. I call that function. Okay. Each object points to a virtual function table, and that virtual function table, contains the addresses of each virtual function, and I get the area from that virtual function. That's why we say that this is kind of an expensive call. Why? Because every time I make a call, I need to look up that function, virtual function table. Okay, so that was the whole idea of polymorphism. But at the end, what do we get? We get this nice reusable code. This code will work for any class that as long as they derive from this shape class. Shape class. Okay, this is as general as possible, because I know that for any shape this has to work. As long as there is an is-a relation between my class and this shape class. Okay, good. Any questions from last week? Somebody last time asked me during the break or after the class, I don't know. They said that he asked me, I think, Mohammed, where are you? Well, half of this class is Mohammed, right? Okay. He asked me, I said that whatever you can do with object-oriented programming languages, you can do the same thing with the C programming language, or even the assembly. How can you do such a thing with the C programming language? I mean, how can you write such reusable code in a C programming language? And I was telling him that just look at this C language QSort function. You know the quicksort, right? The algorithm quicksort. And this is a prototype for the quicksort. So what kind of arrays does the quicksort sort? Do you see the array type? It is void pointer. How many items? It is specifiable. What is the size of each item? It's specifiable. How do I compare the elements of the array? The user has to provide it. So this quicksort implements the quicksort, which is one of the fastest known sorting algorithms, quicksort. So this quicksort was written in 1970s, okay, and after that it has been working for the last 40-50 years, and it did not change. What I am saying is that you cannot get any reusable than this, okay? It is as general as possible. So it is possible to write reusable code using assembly programming language or the C programming language. Reusability is not something specific for object-oriented programming languages. What we are saying here is that if you follow certain rules, certain discipline rules with the object-oriented programming languages, it is easier to write reusable code. We are not saying that it is only possible within the framework object-oriented programming languages. We are saying that it is easier to write reusable code. It is more convenient to write reusable code. That's what we are saying. And some people say that this is too general because it works for all kinds of data types. Maybe I want to restrict it. Maybe sometimes I would say that this should work only certain kinds of data structures. Well, in that case, maybe I should use a object-oriented programming language, and I know that this total area will work for only what? For only shape objects, right? If you are within this hierarchy, it will work. Otherwise, it won't work. So I can make this restriction or generalization as I want. Okay, good. So I think I showed you this, and I sent you an email to watch my video coming to the class. And for the rest of this lecture, I think I will go over the rest of the slides of this chapter. And before that, actually, I have another deck of slides from some other book. That book has a better, more explicit explanation of this employee hierarchy. Let's look at this one. Let's look at the code. And while we are looking at the code, maybe you have some opportunity to ask me questions. Let's look at this hierarchy. Employee class. Okay. I think we did this salaried employee and hourly employee. Salaried employee gets paid by the week. Okay. Hourly employee gets paid by the hour. Commission employee gets paid by the amount that he makes any sales. Okay, commission employee. Base plus commission employee gets some money, some weekly money, plus he gets some commission for everything that he sells. Okay, so of course this is a descendant of an employee, but this is also the child of this class. Okay, so this makes a kind of a more complex hierarchy than we had before, and there is this table for the employee class. I have earnings function and print function. Earnings returns the how much money the employee makes. Print just prints out the information to the screen. So for the earnings of the employee, I don't know, it's pure virtual. Print will be virtual, but it won't be pure virtual. And I have salaried employee. My earnings will be weekly salary. For hourly employee, this is what I'm going to do. If I am under 40 hours, then I just return wage times hours. This is times. Maybe do it this way. This is wage times hours. If hours is greater than 40, then I do 40 times wage plus hours minus 40 times wage times 1.5. So for the overtime, I am paying 50% more. For commission employee, commission rate times gross sales. How much sale I make, and take some fraction of that one. For base plus salary, I have my base salary plus commission rate times gross sales. For the print, for the basic employee, this is virtual, but it's not pure virtual. I print my first name, last name, and the social security number. For salaried employee, okay, first name, last name, social security number, and weekly salary, and it goes that way. Okay, so let's look at the employee definition. Okay, my class employee, constructor, name, last name, social security number. Okay, setters and getters for each. I have my constant keywords. And when I come to here, okay, earnings is pure virtual and print is virtual. But it's not pure virtual. I will implement it, and this is my private section. Good. So let's see the implementation. Implementation is so trivial. Constructor is nicely empty body. I am using the initialization section. Setters and getters, okay. For the print, it's a virtual function. I say get first name, get last name, and get social security. I am not accessing the data members directly. I am using the public interface, which is nice. Okay, of course, for the earnings, I don't have any implementation because it's pure virtual. And that's it. That's it for the whole class. I guess at the end, there should be a... Oh, no, this is not the class definition. This is the CPP file, right? Okay, so let's look at the implementation of the salaried employee. Salaried employee is an employee, so it has everything that the employee has, including name, last name, and the social security number, plus it has weekly salary. So everything regarding the employeeness of this employee will be handled by the base class, but I need to handle anything regarding to this newly added data member, which is setter and getter. Okay, and of course, since I am going to be a concrete class, employee is an abstract base class, right? Why? Why is an employee an abstract base class? Because it has a pure virtual function, which is earnings, right? So employee is an abstract base class, and salaried employee, in order to make it concrete class, I need to provide an implementation for the earnings function. Okay, so I will do that. And of course, I like my print function of the base class employee, but I need to add more information to it. It should print out more information about myself. So that's what I am going to do for this class. So this is my header file. I included the employee.h and nicely guarded. And here is my implementation. See, I did not include employee.h here. Why? Because it is already included in here, right? And even if I do that, even if I copy employee.h and paste it in here, it doesn't matter much because I have the safety guards, right? So I should not worry about if I include it 2 times, would I be in trouble? No, I would not be in trouble. So this is my constructor. It nicely calls the employee constructor to handle these 3 stuff, first name, last name, and set weekly salary, and it just sets the salary using the public interface. Weekly salary is nicely error checked. Okay, if it is less than 0, it is 0, otherwise it is salary, and get weekly salary is a getter. Okay, so let's look at the interesting stuff, which is this one. Pure virtual, now it becomes a implemented function, get weekly salary, and print function. I call the employees print to get to use whatever I have inherited from the base class, and now I am adding this extra information, get weekly salary, so that I print out anything that I know about this salaried employee. And that's the end of the class implementation, I guess, yes. So simple enough. So more important thing here is this one, right? So very simple function implementation. Also, there is a, this is how you use the base class's print function. Good. Okay, you have a question? Yeah.
Yes.
I am kind of repeating this so that you can ask questions, okay? You understand? You should ask questions, yeah.
We have inherited some functions from the base class that is abstract class.
Yeah.
So it would be automatically the abstract class, derived class will be the automatic.
If I did not implement this one, yeah.
If we implement it is.
If we implement it, of course, I am not an abstract class anymore. If I have any pure virtual functions left in my class, then I am an abstract class too. If I have implemented all the pure virtual functions that I have inherited, then I am not an abstract class anymore. I am a concrete class. I can be instantiated. Okay? Good. These 3-4 lines is the reason why I am not an abstract class anymore. Okay? I did not have to implement this print function to become a concrete class, but I have overridden this one because the base classes print function is useful, but it doesn't tell me the whole thing. I need to print out my weekly salary too. Okay. So let's continue with the hourly employee. Hourly employee is this. Hourly employee is same as employee, but okay, I have a weekly wage. Also, no. For the hourly employee, I have the number of hours worked, also the money that I make for each hour that I work. Okay, I have my first name, last name, social security number, my wage, and the hours. And for the sage and hours, I have the setter and getter, and of course these two virtual functions. I have this. What was the C++ 11 way of doing the things? I wouldn't say virtual here. I wouldn't say virtually, but I would say override here, right? Override and override. Here I am saying that these two things are virtual, and I am overriding them. I know what I am doing. Okay, this is old version, but if you are not using a C++ compiler, this is what you're going to do. Okay, so let me do it this way. Okay, again, I'm not going to look at this not interesting stuff. Let's look at the more interesting stuff. More interesting stuff is this. Earnings is this way. I have given you the algorithm already. If hours is less than 40, then I do this. I multiply the wage times hours. Otherwise, I run this formula, which gives me 50% more for the overtime work. Fazla mesai. Okay, for the print again, very similar. Call the print function of the base class, and after that I print my wage and the hours. Okay, good. Let's continue with the third class, which is a commission employee. Commission employee is an employee, but on top of it, I have my commission rate of all the sales that I make. Also, I know how much I make sales. Okay, how much sale I make. Okay, for that one, setter and getter, earnings and print. I will skip setters and getters. And for the earning, I have this one. For the print, I have this one. Very similar to the one that before. And finally, base plus commission employee is a little bit different because it doesn't derive directly from the employee class, but it derives from the commission employee class, right? Base plus commission employee derives from the commission employee, and I have 1, 2. So what are these three things? This is name, last name, social security. This is wage. Is it wage? No. What is this? This is for base salary. Okay, I know that. This one is base salary. I know that this is name, last name, social security. What are these two? Gross sales and the commission. Because this guy is a base plus commission employee. What does base plus commission do? It says that I will have a base salary. You have to pay me every week for some amount. Plus, you need to pay me for the fraction of the sales that I make. Okay, and this one is already will be handled by the commission employee class, but this one I have to handle it. Okay, so let's look at the implementation. So this one, as you see, the constructor of base plus commission employee does not call employee constructor. You should not call the employee constructor here. Why? Because you should call the commission employees constructor, and it will in turn call the employee classes constructor, right? Don't call the base class constructor yourself. What happens if you call? Well, everything will get confused. Don't do that, okay? You should not know if your parent is derived from some other parent, okay? You don't have to know. Well, if you know it, it would be nice, but you should not use that information anywhere. All you are saying is that I am a commission employee. Commission employee might be an employee. It is another thing, but you don't care about that. Okay, you say that I am a commission employee, but on top of it, I have a base salary. So first name, last name, social security number, sales and rate will be handled by the commission employee. Okay, but however it does it, I don't care. But I will handle this salary part. I will handle this salary part myself using the public interface. Okay, so I guess this is the first example that we have seen for this kind of. Well, it shouldn't be a surprise because all we are doing is just calling the base classes constructors and the base classes here. Let's look at the print one. See the print? You could have called the employees print, but you should not do that, okay? Call the base classes print, and this base classes print will call the employee classes print if he wants to. Okay, I am calling the commission employees print, and I will put this get base salary on top of it. And this one is nice too. I am calling the commission employees earnings because I am a commission employee too, but on top of it, I make salary weekly, and I do this too. Okay, good. Any questions so far? So I think I have implemented everything, all the functions of the whole hierarchy, and I am now done with this implementation. Let's write some code to use all these. How many classes? 5 classes. I have 5 classes, right? To use all these 5 classes. I cannot make objects of the employee class, but I can write functions. Okay, I will write functions that will take objects of employee references or objects of employee pointers. Okay, so I can write that, and you will see the examples. Good. Do you think, since you are not asking any questions for some reason, that doesn't mean that you will not ask questions. You don't want to ask questions doesn't mean that you won't ask questions. You will ask questions. Do you think it would have been a good idea to do this? Base plus commission employee is a commission employee, also a salaried employee too, right?
No.
Would that have been good?
No.
Why?
Maybe they will have the same functions, virtual functions.
What do you mean? Maybe I showed you the code.
No. But we, for now, yes, we know. But sometimes we don't know.
That's what I am asking. Is it a good idea to make this one? I am not asking a general question.
Okay.
Is this a good solution? Because this one has already the base weekly salary, right? And this one has the commission. I didn't have to remember this one. This one has weekly salary. This one has base salary. Base salary is actually a weekly salary. Maybe I could have done this. I mean, this would have been a better solution. And for this one, base plus commission employee, I didn't have to add a new private data member. I didn't have to add new setters and getters for the base salary, right? Everything is handled by the salaried employee. So this one is both salaried, I pay him weekly. Also, I pay him by the amount that he makes sales, right? I could have done it that way. Let me try to base plus commission employee. Let me try to change it a little bit actually. So it's going to be a salaried employee. So it will have set weekly salary, get weekly salary, whatever. So how do I do that? How do I do that? Okay. Hourly employee, commission employee, and base plus commission employee. It will be public commission employee, comma, public salaried employee. Okay, salaried employee. And then what do I do? And then I would get rid of this line 21. I would get rid of these two lines, right? I don't need them because I have my salary, get weekly salary, set weekly salary, right? I have those. What else? Okay. I need to call commission employees constructor. Also, I need to call the constructor of the weekly salaried employee, right? But I am sending the first, last, and social security number for both of them. So that means that I have two employees in me. Okay. So to prevent that, C++ comes up with some solution. Because remember, if I do this, what was the slide number 60? Yeah. If I do this, remember inside my employee, I have name, I have last name, and I have SSN, right? So I am inheriting these three things two times, once here, once there. Okay. To prevent that, C++ says that, okay, you need to use this notation. But this is not talked about in the book, but I need to switch my keyboard now. Okay. Okay. Let me show you an example. Where is my example? Okay, that's the problem in here. If I do this two times, I will get the base class data two times, and that will be a problem. To prevent that one, I need to do this. Okay. Base, I would say public virtual base and public virtual base. Okay. If you do that, the compiler is smart enough to eliminate those kind of problems. You are adding more tasks to the compiler. Okay. When you say, I am including this base two times, virtual base class, then you need to be careful about the things that will be inherited two times. Okay. That's what C++ does. And I am not going to talk much about it. And the book did not do that. They did not choose this way doing things because they did not want to go into that trouble. But we could have done it that way. Okay. So public commission employee, public salaried employee. But before them, I would have said public virtual employee for the commission employee and the salaried employee. Okay, so that would have been a good solution. I think I liked it. In fact, you can do it yourself and test it yourself. Good. Okay, so let's write some driver code. Let's write some driver code to test these classes out. And this is what I do. I include salaried employee, hourly employee, commission employee, base plus commission employee. And in fact, I didn't have to include this employee.h, right? Because it is already included in any of those. And I have two functions. See, the function takes not objects of employee, but pointers of employee, constant pointer. And I'm not going to change that pointer either. And I have a constant employee reference. I know that nobody can make objects of employee class, but I know that it is possible to use is a relationship to send objects of salaried employee, hourly employee, commission employee, or base plus commission employee. And okay, and this is my main function. I make one salaried employee, hourly employee, commission employee, and base plus commission employee. Okay, I have 3 objects, and I am calling the print function on all of them. Remember, print is a what? Print is a virtual function, right? Since print is a virtual function, there is a possibility that whenever I call this print, it might be a polymorphic function. It might be a late binding function call. So line 43, is line 43 a polymorphic function call? It will be decided during the runtime or compile time. Runtime or compile time. Line 43, 45, 47, 49. They all will be compile time. Why? Because for polymorphism to happen, for late binding to happen, I have to call those functions either through the base classes reference or base classes pointer. I am calling them directly. So these are static function calls. They will be decided during the compile time. Okay? These are efficient function calls, but these are not flexible. Okay? And I know that these are not base classes. Well, maybe, I mean, remember, this commission employee is a base class for the base plus commission employee. It could have been a base plus commission employee object for this one, but I know that this is not a base plus pointer. This is not a base plus reference. So all 4 of them are static function calls. They will be decided during the compile time, not runtime. Okay? You have a question? Half a question? You are not going to do that? Okay. So let's try to make some polymorphic calls. I have a vector of employee pointers. Okay. And 4 of them, and I put my objects in them, their addresses, and I have a loop from 0 to size, and I call this virtual via pointer function. It takes pointers of the base class employee. Okay, so let's look at that function. Actually, that function takes a pointer to the employee base class, and it calls the print. I know that this is definitely a late binding function call, polymorphic call. Why? Because employee is the base class. Okay, base class pointer is a base class pointer. Okay, and I am calling the print function, which is a virtual function, to a pointer. Okay, so this is definitely a polymorphic call, late binding call, similar to this one. Definitely a base class call. Definitely a polymorphic call. Okay. And the second thing is the same thing again. A reference to the base class. This print and this earnings, these 2 function calls are polymorphic calls. Okay. I mean, again, the example is a useless example. Why would I do such a thing? Just to show you what is going on with these kind of function calls. Late binding. But these are early binding examples. Good. And I am making this call, and I'm making this call. Every time this function is called, okay, the meaning of line 85 changes. It depends on the type of the object pointed by this base class pointer. Sometimes it points to a commission employee. Sometimes it points to a base plus commission employee. Sometimes it's a salaried employee. I don't know. I will make that decision during the runtime, similar to this one. But for this one, I definitely know salaried employee is a salaried employee. Okay, I definitely know that one. This print function is the salaried employees print function. Okay, good. Any questions? Okay, so as I said before, I mean, understanding inheritance is not that difficult. If you read the book, if you listen to me, try to write your code yourself. It is not that difficult, and the important thing is that why we are doing this. Okay, we are doing this just to remember that our employee class doesn't make much sense by itself. But if you use it as a base class for the other or all the other classes, it starts making some sense. Okay, so the function of the employee class is to collect all the common features of all the employees together. Nice encapsulation example, but employee class doesn't make a concrete class by itself. If you use it as a base class, then it makes the jobs of other classes much easier because I am calling the print function of the employee class from the other classes, also the constructor too, right? And on top of it, I can write these kind of functions that takes employee references or employee pointers. So during while I am writing the other code, it makes it possible to write general code. See this function at line 83 or 91. These two functions, they don't depend any other classes other than the employee. Okay, so these are in this hierarchy. These functions are as general as possible. They are as usable as possible because it is possible to use them with any kind of employee class. Yes.
Is it better to use static functions because the program is limited, or this inherited type of functions for this example?
For what function? For what function you mean?
The static functions that 2 slides ago, or 4 of them. We can do the same thing with.
You mean that I can call them using a base point? Well, if you know which print function you are gonna call during the compile time, of course it is better to call the static ones because you are helping the compiler, right? You are saying that if you don't want to make any polymorphism happen, okay, then of course you use this notation. But if you don't know during the compile time which functions to call, then in that case, of course, you'll have to switch to polymorphism. Polymorphism is more expensive. That's why you need to be careful about it. Okay? The meaning will be decided during the runtime. But if you need it, don't try to avoid it. Use it. Okay, good. So the question was if I have a choice between static and non-static or late binding and early binding, and if it doesn't make any difference between early binding and late binding, of course choose the early binding. It is more efficient. Okay, good. So let me go back to by the way, this, I think there was a very nice, okay. So this is my employee vector. Remember my vector of employees. There are 4 of them. There are 4 pointers, and each one is pointing to an object. Okay, each one is pointing to an object. This one points to a salaried employee. This one points to an hourly. This one points to a commission. This one is base plus commission employee. Okay, 4 of them. Okay, and each object in itself has a pointer to a V table, virtual function table. Inside the virtual function table, okay, there are 2 functions because in my base class I have 2 virtual functions. And each object points to this function table. When I make that call through the base pointer, I find this function table. Inside this function table, I find my function and I call it. So when I do this, hourly employee base class pointer, hourly employee print, I follow this link, base class pointer. I find my object. From this object, I find the address of the v table. From the table, I make a search to find the print function's address, and I take that address, I make that call. So 1, 2, 3, 4, 5 steps to make that function call, which is expensive, as opposed to just 2 steps, finding the address of that function and calling it. Okay, good. Let me go back to my book slides now and see what the book says remember the last time that I talked about pet classes. Let's see those pet classes again. Okay, so did Erdoğan Hoca talk about this override keyword? Okay, so this is in the book. We say that in C++, we have this new way of saying that. Okay, in my base class, okay, this function bill is defined as virtual. In my derived class, when I override this function, base class function, virtual function, I say that I am overriding it. Override is a C++ keyword. You tell the compiler that this function is an override of the base class virtual function. Okay? So you are telling the compiler that I am overriding. If you put override here, and if this function is not virtual, you will get an error message from the compiler. Compiler tell you that you cannot override a non-virtual function. Okay? So this is just to make things explicit, just to make things more clear for the compiler that I am overriding it. What happens if I raise this one? Would this code compile? Yes. So why did I use it? Same reason as this const, right? What happens if I remove this const? The function build doesn't change anything, it will compile, right? But I put it in anywhere just to make sure that I do not change anything inside this function build. Okay. But am I correct when I say if I remove this, would my code compile? The function build would compile, yes, but anybody calling that build, okay, may not compile because, is that true? If I remove this const keyword from here, the function build compiles, yes, I know. But anybody calling build may not, because if I have a constant object sale, I cannot call bill on that sale object, right? If the object sale is constant, then I cannot make that function call. Okay, but as long as I am concerned with the function bill, removing this doesn't make any difference. Anyway, I put this const for the same reason as I am putting override here. It is helping me to get more compiler help. If I make a mistake, compiler will tell me that I am making a mistake. This is not an override. Also, it makes this function more readable. This is definitely a virtual function, and I am overriding it. So C++ override keyword. Another C++ keyword is the final. Final says that this is a virtual function. I know, okay, I am going to use a virtual, but I don't want any class derived from myself. I don't want any class derived from myself to override this function bill. Okay, so this is my final version of this function. It will not be overridden. Nobody is going to override this function bill. Okay, after myself. Okay, I define it. You may derive yourself from myself, discount sale, but you will not override it. If you override it, compiler will give you an error message. Again, final keyword in C++ is helpful if you like to achieve this capability. Good. Any questions? So I think Erdoğan Hoca, maybe he talked about this, but he didn't give you the keywords. There is nothing to it, just 2 new keywords. final and the override keywords. Good. Then I am moving on. Then in that case, if I don't have any questions, we talked about this before actually. If polymorphism is such a good thing, why don't we use it all the time? Because it has overhead. Remember the table that I showed you? It has to follow the link, find the object, find this virtual table, scan the virtual table, find the function and call it. Okay, so it is 3 more extra steps than calling a regular function. That's why we don't. It takes more memory for the storing the virtual table. Also, it takes more CPU time. So we don't like it. If we don't need it, then we shouldn't use it. But if we need it, if it is useful, then do not hesitate to use it. Okay, we talked about pure virtual functions. Pure virtual function is a function that is not implemented. Who asked me this question? Why are we doing? What did you ask? You asked the question. What was your question again?
Why do we put it one instead of just pure virtual?
Oh, yeah. The question was, why don't we invent another C++ keyword named pure and put in front of virtual, just pure virtual void draw, kind of. That was the idea. Well, they make this decision that way. Usually you don't want to introduce many new keywords to your language. Okay, keywords means that you cannot use that keyword as an identifier, as a function name, right? As a variable name. So it becomes reserved. You cannot use it. So virtual was already there. Okay, so they introduced it. They didn't want to introduce anything new. In Java, you don't say equals 0. You will say abstract virtual void. Java has a keyword abstract.
Can you say equals 5 or 10 or something?
And I mean, the meaning of this one is kind of, you know, in C or C++, each function is a pointer, right? The draw is a pointer, okay? It points to the function beginning. When you say equals 0, it's kind of equals null. So I don't have an address for this one. No, you don't get to say 5, okay? But you may say that I have a function pointer, okay? Void f, okay? F is a function pointer that returns a void. It doesn't take any parameters. So you may assign later f gets the value of draw. Okay, I mean with the C syntax, of course you could. This is address. Okay, of course you could do this kind of assignment, function assignments, but I mean this is kind of that meaning. Okay, I am saying that I am giving you the address of this function, so the address of this function is null. That means that there is no such function. It kind of means that. Okay, it's a good thing to question why did I make this decision, but most of the time I cannot give you a good answer. Somebody was asking me the other day, in Turkish when you say hiç kimseyi görmedim, hiç kimse is negative, görmedim is negative. That means that when you say hiç kimseyi görmedim, herkesi gördüm. Isn't that the same thing? You say no, but that doesn't make sense. Yeah, it doesn't make sense. How do you explain it? I don't explain it. We use it. Okay. So sometimes with the languages, natural languages or these kind of languages, we don't ask those kind of questions. Just shut up and use it. That's how it taught me. Okay. Okay, abstract-based classes, again, the idea of abstract-based classes is actually difficult to explain. Why would you have a class that doesn't have an object? How could it be useful? Well, of course, it is useful for these kind of purposes. Using the abstract classes, you can write abstract code, okay? Once you write the abstract code, that code would be very, very reusable, such as this one. This is a very, very abstract code. When you look at this one, so confusing. What kind of data does it sort? We don't know. It will be decided during the runtime. What are the sizes of each object? How do you compare the objects of that class? Okay, those objects. So it will be decided during the runtime. This is a very, very abstract code, but it's a very reusable, very nice code. Okay. Oh, okay, I am out of time. Any questions? Let's take 10 minutes of break. After the break, I will come and I will finish up with this chapter.
Abstract base class zaten başlı başına güzel bir şey. Ciddi bak.
Kalktım baba karanlık kalktım. Yanlış kalktım ya ben. Yine yanlış kalktım. Yapıyorum karanlık kalkıyorum karanlık. İngilizce ne ya? İngilizce
Kardeşim biz zamanında çalıştık biraz da 555
efendim yerine İstiyorum ben yabancı. Sürekli nasıl çalışıyorum? İngilizce kaç kurs vardı?
İlk güzel işte ilk güzel şeyde o ilk güzel pardon ilk gün şeyde değil bu Almanya'dakiler
Şunun gibi.
Şey üretemezsin. Popülasyon yönetici
Perşembe günü işte genelde şey olur. O yüzden dersleri sana girecekmiş.
ne var? Hakan da izledim.
Şey konferansa girmiş.
Hayatım.
Derslere
Hayatım.
derslere ya da başka dersler gönderdi.
Abi girmez. Girmez. Çalışıyoruz.
Bunun bir şey var. Perşembe günü şey yok.
Tam girmiyorduk ki zaten. Acı bir gerçek mi? Zaten önce kırmızı nokta. Çizgi.
Kırmızı nokta böyle yandan geliyor.
Uykum var.
Para kazanmak
Birine göre yapması gerekiyor.
ben şaka alıyorum.
neyse biz
Şey değil sana böyle fonlarından
Gözünü şöyle gelirsen. Allah çeksin. Sana mı çıkıyor? Ya da dur cebime para var zaten. Şurada çok konuşma. Hayır. Olacak zaten. Tamam demiyorum.
ne diyorsun?
faizli değil mi?
Gelmek.
Kaybedebilirim. Ama
Niye?
banka zaten şey kredi yani losa girmez. Yani emin olmadığım
Ufak hiçbir şey değişmeyecek.
girerse zaten
Çok çok iyi para. Niye abi?
28 yıl
Nasıl?
28 bin.
Çok.
Olmayacak işte sorun o.
Hayır.
Bunu böyle yapacağız ya.
Bir seneliğine koyarsın. Oraya
$6,000 ne kadar?
Sonra bu objeden
benim oyunumda çalmaya çalışıyorum.
7 sene yaşarım.
Hadi en arkada.
Gerçekten geçen sene benim şu an
Yok be oğlum ki bıçağı mı zaman karanlıktan
yok ya buradan bir şu an
karanlık.
Orada 2 lan galiba. Yok ben 1.75 tam.
Ne kadar yani.
evet.
Burada
Ya hayır.
Marketlerde bile
bu ne olacak?
1.75 şu.
Bizim oradaki market
Ne olacak?
Orada 1.75
En fazla bir tane son puan var. Şey diyorsun sen.
Zaten vazgeç.
Ayakta duramıyorum. Bu objektin çağını görüp onun işte dersi zora Işık yanıyor. Yine dolmuş yapıyor. Ama siz kardeşiniz
Değişik aslında. Şifayla Ha, o şeye geliyor. Tamam, sen şey diyor. Gebze'nin içine giriyor. Görüyor musun normalde? Gelip.
Yerim çok şey yapıyor.
Tam kuzeye
Şıs şey ısınır.
şey mi? Türkiye beşirmiş mi? Şekerler girdi. Mümkün girdi. Görecek söylüyor.
Yerine geçiyor. Aynen.
O zaman adam bu boyuna çıkıyor ya.
ben 75 ben şu an buradan göremiyorum.
Şöyle o karanlık görüyorum.
Şey sorun
Bu bir tane mi? Bir değerin boyutu.
ha o şeyin yaptığı cam yapmış.
Onun gündüz ne oynuyor sence? Oynanıyor. Şöyle değil mi?
Yok zaten bütün adam
Ha, o sıfır o zaman bir şeyde oynayacağız.
hala göremiyorum.
Kanka biraz sağlayayım.
Şey çare.
Yok mu? Şeyler var.
Çok gelişiyor.
Ama şey yapacaksın. İlk adet, birincisi ilk adetini milyon alır. Bir tane yer alırsın. Hierarchy örneğin onun boyutundan bir fazlası kadar bir tane point ölçüyorsun, yapıyorsun. Onu oraya kopyalıyorsun. Bir tane boş kalıyor. Diğerinin de o boş kalan diğerinin ilk adresine atıyorsun. Sonra diğerinin ilk adresine bir fazlasını bir daha çağırıyorsun.
Aynen anladım. Denedim işte bayağı ama bir şey segment fault yedim veya kopyalamadım. Çoğu oldu da işte onu yapamadım. Şunun deliliği abi çok
Bakalım bırakmıyor.
çok iyi.
Bırakıyormuş.
Al senin olsun benim için. Microsoft mu? Aynen Surface. Sivas'taki anılarını anlatacağım.
Nasıl yaşıyorsun? Sevmedim.
Üç kişi birleşik bilgisayarda oturuyordu.
Oğlum beni ayağım sıcak.
Camı açalım mı? Sen camı bayağı cam var. Sen orada mı oturuyorsun?
Benim de bir ara çok zorlandım sonra hemen bir şarkı açıyorum falan.
Okay, so abstract base classes, as we said before, their main function is to serve as a base class for the class hierarchy. Also, when you write your code, what was the rule again? Remember we said code against the abstract classes. If you write your code against the abstract classes, that means that any class derived from the abstract class is applicable for your code. Okay, that's what we did with the those two functions. Remember, remember these functions, the total area function. I have written this function using only the information that I got from this shape class, right? From the shape class only. That's what I did. I didn't use anything specific about circles or rectangles or triangles. So this function is applicable to this whole hierarchy because I have written this code against the shape class, which is an abstract class. So so that's the name of the rule. Where was I? Okay, here it is. Abstract code against abstract classes. Okay, so that's why we are using abstract classes. If you can come up with abstract classes like the base classes, then that means that you are preparing your framework to write reusable code. Okay, so I think there was an example in the book, and I think that I talked about this extended type compatible to my section, but I think Erdoğan Hoca did not go over the book slides, and I am doing that. I say that if I have a circle object, I may assign a circle object to another circle object, triangle object to another triangle object, because there is type compatibility between them. I know that. But there is this new concept of extended type compatibility. Since there is an is-a relationship between circle and shape, triangle and shape, if a function is expecting a shape pointer and I have a circle object, it is possible to send the address of this circle object to this function. Okay, why? Because there is a relationship, and there is an extended type compatibility between the circle pointer and the shape pointer. Circle is a shape. There is a relationship between them. Okay, and there is this extended type compatibility between circle and shape. Circle and shape. Okay, this is called extended type compatibility. And for this one, without doing anything, I just send the address of circle to this function which expects a shape pointer. I can't do the same thing. Let me write another function. Let's say I have another function named g, and it expects, let's say, a circle object. Okay, circle pointer. Okay, and let's say my base class is not a abstract base class, but it's a base class, concrete base class. Let's say I have this shape S. I can't do that. Okay, I can't do that. This is not possible. There is no type compatibility between those two classes in the other way. Okay, I cannot send an S, address of a shape, to a function that waits for a circle pointer. This is not possible. Okay, there is no extended type compatibility between them. So it's a one-way relationship between these two classes. Circle is a shape. Shape is not a circle, not necessarily. Okay, good. So we will come back and we will talk about this. When I say not necessarily, I will explain it. Okay, and I think last time we looked at this one. I think this is okay. Let me try to explain this from the beginning. Actually, erase everything. Okay, so much cleaner now. So I have a class named pet. Okay, evcil hayvan pet. And this is a very simple class. I don't have any private sections for the sake of simplicity. Okay, each pet should have a name, and I have a virtual void print. Okay, it prints out the name of the pet. And I have a class dog. It derives from pet. On top of the pet's feature, which is a name, okay, string, it says that I should have a breed. Okay, I should have a breed. So let's try to write some code using these two classes. Both of them are concrete classes. They are not abstract. So I can make objects of them. Let's say I have a pet, okay, P1, maybe a pet 2, maybe a pet pointer, PP, okay. And I have dog objects, D1, D2, maybe a dog pointer. Okay, so let's draw some memory configuration to these. So P1 is here, P2 is here. For P1, maybe let me make this smaller and put it in this corner. more readable code maybe. Okay, so let me do this then. P1 dot name gets the value of for my pet. I don't know what kind of name it is. Let's say it is. Let's say that pet is a cat. Name is Boncuk. Okay. So inside this P1, I have the name field as Boncuk. Okay. So for P2, I don't know. For P2, I didn't do anything. Let's say P gets the value of address of P1. This is PP. So address of P1, that means that this one is pointing to this part of the memory, right? That's what I did. So let's do this dog one. D1 dot name is Karabash. So it's a dog, so it is Karabash. And D1 dot breed. What is the type of? Kangal is not Karabash. Karabash is not Kangal. It should be something. What? Give me another. Anatolian shepherd dog. Okay, shepherd dog. Okay. So let's say this is D1. Yeah, çoban köpeği. Inside D1, I have for the name Karabash, and for the breed, I have shepherd. Okay. So how about this DP? DP gets the value of the address of D1. So DP is this. So far, I did not use any extended type compatibility. I use whatever I have knew before. If two types are the same, then I can make the assignment. No problem. Okay. Let's say I could have said P1 gets the value of P2. No problem. So when you say P1 or P2 gets the value of P1. Okay. In this case, P2 is this, right? And I could have done the same thing again. D2 gets the value of D1. Okay, this is D2, and D2 becomes name and breed. Okay. So didn't use any extended type compatibility. Let's use some extended type compatibility. I can say, if I like, I could say this is possible, right? I think I'm gonna make this a little bit smaller or move it up. Maybe I will need more space now. Okay, so let's do this. I like to use this pointer to point to, let's say, pet pointer. Can I do this? Pet pointer takes the address of D1. Can I do this? Each dog is a pet, so I could show the address of each dog using a pet pointer. Yeah, it is possible. So instead of doing this, now I am going to do this, right? So PP is pointing to a dog, right? I could do that, no problem, right? No problem. But I can't do this. Dog pointer gets the address of P1. This is not possible. There is no extended type compatibility in here, right? So I can't do that. I know this because is a relationship is not both-way relationship. It's a one-way relationship. So this is not possible. But I know that PP points to a dog object. When I say cout PP, okay, PP and name, it will print what? What does this print? It will print Karabaş on the screen. How about this one? Cout PP breed. What does it print on the screen? PP points to a dog object. Karabaş I printed. How about the breed part? Breed part is the shepherd. It will print shepherd. No, it won't print anything. In fact, this is a compiler error. Why? Because as the compiler say that, okay, PP is a pet pointer. Where is the pet class definition is here. Do I see a data member or the function member named breed? No, no. So this is a compiler error. It's a compiler error. How about this virtualness and that kind of stuff? How about if I define them later? Virtuality or overriding something happens, but I override the same name thing, okay? I override the print thing. Print is already there, okay? When the compiler compiles this stuff, compiler says that I'm looking at the definition of the class, okay? I am looking at the definition of the class. Is there a field or data name named breed in there? No. So I will just issue an error message. This is different from this one. Cout PP print. Whose print is going to be called in this case? Dog's print, right? How did I know that? Because PP is a pointer to the base class, and print is a virtual function, and now PP is pointing to a dog. I know that dog's print will be printed, so it will be executed. No problem with this case. How about this one? How come did this happen? Print is a member of this class, pet. I know that it's virtual. I know that it is compilable. This function is possible, but I don't know which function to call during the compile time. But I know that during the runtime it will come. But this is so different. This one says that there is a field named breed in my object, and when I look at it, no, there is not. So this is a compiler error. This is not. This is a perfect function call, polymorphic example, and this has nothing to do with it. Okay. So the difference is very, very different between them. But it might seem like, I know in this case, I know that PP points to an object that contains a breed field in it, but I cannot reach it, right? Using this pointer. I know that PP points to an object that contains breed, but I cannot reach it. Compiler doesn't let me do it. Okay? Compiler doesn't let me do it. Okay? I know this one. Can I force the compiler to do it? Ask the compiler to give me the breed part anyway. The answer is yes. You may ask the compiler to convert this pointer to a dog pointer, okay? And if there is a real dog object that is pointed by this pointer, then I will do whatever I want, okay? So in my case, pet is the base class, and from pet I am deriving this dog class, and there is a relationship. Whenever I need a pet object, I could use a dog object in it, okay? But whenever I need a dog object, I cannot use the pet object. Making an assignment from down part to up part, making an assignment this way is okay. Okay. This is called upcasting. Upcasting is always okay. Upcasting. Because I am using my is a relationship here. Upcasting is always okay. Making an assignment, trying to make an assignment this way is called downcasting. Downcasting. And downcasting is not allowed. You cannot do downcasting directly. But if you know what you are doing in this case, I know that this PP shows a dog object, and I can ask the compiler to do this downcasting for me, okay? To do this downcasting for me, because I will convert that pointer. And if it is possible, it will make that conversion for me. That's called downcasting, and downcasting is a special operation. Upcasting this is what I did, upcasting, okay? I assigned a dog pointer to a pet pointer. No problem, upcasting. But if I try to do just the opposite, try to do the same thing with the other way around, other pointers. It's called downcasting, and for downcasting, I need to use a specialized notation, and I'll show you how to do that in a few minutes. Okay? Good. So last time I think I talked about this, and last time actually I did that too. I mean, I was very careful about using the pointers, but not the objects themselves. Since I could do this, how come can I do this too? Maybe do this, right? P2 gets the value of D1. Since this was possible, upcasting, right? No problem. This should be possible too. So what does it, how do I do that? So P2 is here instead of Boncuk. How about D1? D1 is here, right? So I will copy name part to name part, Karabash. Okay. But the breed part, there is no space to copy the breed part in here, right? So I can't do that. So, well, it is possible, but it's kind of, maybe I should put this in quotes, right? It is possible, but there is this problem happening. It's called slicing problem. Maybe use a different slicing problem. I am slicing my object, and I am only assigning part of this object. Dog1 has more than just name. It has the breed, but there is no place to put breed in it, right? So the slicing problem is happening here. When I do this assignment, okay, slicing problems happening. Previously, I did not have this slicing problem because when I make the pointer assignment, the object doesn't get sliced. The object is there, right? I am still pointing to that object. I did not use any data. I did not lose any data. Of course, using this pointer, I cannot reach that breed field. I cannot, but the data is there. Data is there, I know. But in this case, slicing is happening. When I do this assignment, it is possible with the ISA relationship, but I am using some data. So usually we don't use our ISA relationship, extended type comparator, this way, but we prefer it this way. Either the pointer assignment or the reference assignment. Yes?
If we use some data using this relation, why didn't they forbid us from using it?
Well, it is possible. If you like to use it, if you don't need the extra part, you can do it. Okay? So there is something going on, and you should be careful about what is going on. Okay? You are losing some data. If you don't care about what you lose, then you are okay. But if that's important, then you should be careful about it. Okay? And if that's a problem, don't do this kind of direct object assignment, but use pointer assignment or the reference assignment. Yes?
When a slicing problem occurs, is it like the compiler doesn't copy the part that is going to be lost entirely, or is it just put it in the memory and it's just unreachable?
No. It just doesn't copy. It just doesn't. You know what happens here? When I see P2 gets the value of D1, this D1 is automatically converted to a pet object, and pet object is assigned. Okay? So you are saying that the shepherd is copied somewhere there, so that would cause some memory problems. No. Okay? So usually nobody does it this way. This is very, very rarely done. What we do is this way. So far we did this way all the time. Remember those two functions that I called virtual via pointer, virtual via reference. Also all the vectors that I have used for my global functions. Remember all of those? They were all taking pointers to the base classes, right? So I did not use direct objects themselves. Okay, good. So for the slicing, sometimes, I mean, maybe we shouldn't call the slicing process a slicing problem. It's a thing, it happens, okay? It's not a problem, it's a feature, okay? So think about this way. So slicing occurs, and if you don't want the slicing to occur, then use references and the pointers. And I mean, for the functions, we don't take the objects directly anyway, right? We don't, for the functions that takes objects, we use either pointers to the objects or the references to the objects. So there is not much opportunity, or there is not much case for the slicing problem to occur anyway. But you should know about this, and you, this makes us more knowledgeable about what's going on with the extended type compatibility between the base classes and the extended classes. So let's go back to this one. I know that this PP points to a dog object, but I cannot reach the breed field of this object because the type of PP is pet. Inside pet there is no breed. So let me do this again. Okay, since I keep making this smaller and smaller again, okay, I will push it up, make it a little bit smaller, and okay. Same thing, I will take this one. This was okay. Duplicate it. Okay, let me start from here again. PP points to a dog object, and I know that I can't do that. But can I do this? Dog pointer gets the value of pet pointer. No, I can't, right? I can't, because there is a relationship. It doesn't work that way. I mean, I know that from this relationship, right? I know that pet points to a dog object, but I can't make this assignment directly. Although I know that PP points to a dog object, I cannot make this assignment directly because the compiler doesn't know that during the runtime it will always point to that one. But I can force the compiler to do it anyway when I say dp. Okay, remember the static cast? I will say dynamic cast. Okay, I am going to force this to be a dog pointer and PP. I am telling the compiler that take the pet pointer. Okay, this one. Take that pointer and cast it to be a dog pointer if the object pointed by that PP is really a dog object. I follow the object, okay, I follow the pointer, I find the object. If the object is of type dog, then I make this pointer assignment, okay? I make this assignment. If the assignment is doable, that is, if this object is a dog object, this assignment is done. If the object is not a dog object, then the assignment will be done, but a null pointer will be assigned to this DP. Okay? So not always I get a valid assignment from this dynamic cast operation. Okay, this is a operator. It's like a static cast, but it's dynamic cast. Okay, type casting. I am trying to cast this pointer to a dog pointer, but it only happens if this pointer is really pointing to a dog object. Okay, so that's why we call it dynamic. It depends on the object that I am pointing to. Okay, in this case, I know that PP points to a dog object, and DP in this case will point to the right object like this one. Okay, no problem. How about this one? When I say PP gets the value of P2, okay, now PP points to here, and when I do the same thing again, duplicate and make this pointer assignment. In this case, DP will get null. Why? Because I know that, okay, I know that PP points to a pet object, not dog object. When I make this assignment, it will be null. Okay. So upcasting was okay all the time. Downcasting sometimes works, sometimes doesn't work. All the dog objects are pet objects. I know that. But not all pet objects are dog objects. Okay? This way, the assignment from down to up, upcasting is okay. But downcasting, I need to be careful. Okay? The direct downcasting is not allowed. If you are doing downcasting with the pointers like this one, then it depends on what you are pointing to. Okay? What you are referring to. Okay, sometimes I have to do this. Sometimes I have to do downcasting to write some specific code. And we will see some examples. Yes?
We are using the reference operator to assign D1 to PP.
It's not reference operator. It is address of operator.
Yeah, we actually, what we did is actually made them allies of each other. Is that true?
No, this is the address of operator, okay?
No, I mean the upper one.
This is the address of operator too.
Yeah, address operator.
Yeah.
What if I want to copy of the D1 to PP?
You like to copy D1 to
PP.
D1 is an object, PP is a pointer. You cannot do that. D1 is a object. D1 is this, is an object. PP is a pointer. If you do that, yeah, you could. I mean, if you take the address of D1 and let it to PP, yeah, this is allowed. This is no problem. I did not understand what you are asking actually.
I assume that just PP is an object of the base class.
No. This is what I did before. PP is a pointer. DP is a pointer. P. Okay.
Okay, what if I did P1 assigned to DP or D1?
P1 assigned to.
D1 or.
I did that already. P2 assigned to P1. That's an object assignment. That's like assigning two integers together.
No, I mean P1 is an object of text, and I want to.
Just tell me what should I write. Just tell me what should I write.
Oh, P1.
P1 assigned to
D1.
P. D1. Okay, I did this. P1 assigned to.
Yeah, we did it, but you said it is not efficient, and we are using the.
I mean, you mean this one? You mean the slicing thing?
Yeah.
Yeah, slicing happens. Yes.
Yeah, but I want a copy of the D1.
D1 to P2. What do you mean? I mean, I did that already. I mean, you like to make a copy of D1, assign it to P2. Yeah, it is assignable. There is an ISA relationship, but slicing occurs.
We don't like it? You said we don't like it?
No. I mean, I didn't say we don't like it. That's why I don't want to say it's a problem. That's why I didn't write it in red. I said that you are losing some data because there is no data field inside P2 to hold the breed field, breed data member, right? So breed will be left out. If it is okay with you, then it's okay. But you should know that you are losing breed. So all you are asking is slicing problem, not pointers. I mean, whatever you are asking is not related to the pointers. It is about slicing. Okay? So let's go back and let's try to use this downcasting in a useful way. Okay. Let's try to use this downcasting in a useful way, and I will go back to the other set of slides. Where are my other set of slides? Yeah, here it is. I think I have some code, dynamic cast. Okay, so this is my main again. I am using the same hierarchy. Remember the hierarchy that I showed you? Employee hierarchy. And I am doing this. I have, again, 4 employee pointers. Okay. I have 4 employee pointers. 1, 2, 3, 4. And I made this vector. And I am from 0 to employee size. And each time I call this employees I print, it's a polymorphic call. It will be late binding call. Yeah, I do that. How about this one? Line 50 to 52. Take each employee pointer and try to cast it to a base plus commission employee pointer. Okay. I know that in my vector there are 4 objects. This one cannot be typecasted because base plus commission employee cannot be typecasted to salaried employee. Let's try to draw our hierarchy again. Employee, salaried employee, commission employee, hourly employee, right? And I have base plus commission employee, right? So this salaried employee is a salaried employee and employee. I cannot convert this pointer to a base plus commission employee. I know that, right? So the first one cannot be converted. So this will return a null pointer. And if the right pointer is a null pointer, then I will continue. Okay? So the second one, hourly employee, cannot be converted to a base plus commission employee. Again, it returns me a null, and I will continue. And then the third one, commission employee, again, cannot be a base plus commission employee. So I will continue. The last one is the base plus commission employee. So my right pointer, okay, will point to the same object as this employees 3, the last element of this vector. And it will not be a null pointer. So my right PTR, what is the type of the right PTR? What is the type of the right PTR? Base plus commission employee, okay? This one. So when I say the right PTR, okay, see, the right PTR get base, does it work? Does this work now? Line 58? Get base salary, because why? Because for the commission plus base plus commission employee, there is a get base salary function, and I call that function. I get the old base salary. See what I am doing here. I get the old base salary. I multiply it by 1.10, and I set it to set base salary, and I get the base salary just to print it out, and I finish out the if statement. Okay, and at the end I print out my earnings. Again, this is a polymorphic call. So this piece of code works only if my current element inside this iteration is a base plus commission employee, right? This is a very generic code from line 44 to line 66. It works for all kinds of employee objects, but this part of the code works for only base plus commission employee objects. Specific code. This is not general. So this is not a very good code. Why? Because this part of the code depends on the base plus commission employee class. But sometimes I may like to work that way. Okay. Sometimes I like to be dependent on the concrete classes. Okay. And if you like to do that, the way to do it is doing, okay, downcasting from the base class to the derived classes. And for downcasting, you need to use this operator dynamic cast. Okay, it's like static cast. Static cast, you know why we call it static cast? Because for the static cast, you always know during the compile time, you always know the result. For dynamic cast, you need to look at your data during the runtime. It depends on what kind of pointer you are using. Okay, what kind of object you are pointing to, and at each iteration, this would return either a valid pointer or a null pointer. If it's a null pointer, I don't go into this loop, this if statement. If it's a valid pointer, then I will go into this one. Okay. Good. Question. The right pointer. What is the value of the right pointer? The right pointer is the same as 1, 0, 1, 2. Employee is 3, right? The value of the right pointer is the same as employee is 3, right? It's the same thing, right? It's the same thing. Can I do this? Employees I. See, I downcasted employees I to the right pointer. I know that employees I is pointing to a base plus commission employee object. Can I do this? Employees I get base salary. Their values are the same. They are pointing to the same object. Can I do this? What? But there is a relationship.
If it is automatically downcasted, you can.
Typecasting, downcasting is not done automatically. If it is done automatically, then you have a compiler. No. Can I do this? I asked the same question again before. Remember when I say PP arrow, breed? I couldn't do that, right? Why? Because even though I know that PP points to a dog object, I cannot refer to the breed part using the pet pointer. Pet inside the pet class, I don't have a data named breed. Again, employees what is the type of employees? Employee pointer. Inside my employee class, I don't have a function named get base salary. The compiler will tell me that no, you can't do that. But I know that write PTR is the same as employees I. Yeah, I know. The compiler doesn't think it that way. So what do? I did is downcasting. I made sure that right pointer is pointing to a valid base plus commission employee, and I continue doing this. Okay, I continue doing this. I get my object, write PTR. Now I can treat the write PTR like a base plus commission employee because its type is base plus commission employee. Okay, I handle everything regarding the base plus commission employee. I think they are getting some kind of a raise, 10% raise, all the base plus commission employees. The rest of them are treated the same. Okay.
John, we can do here instead of derived pointer, derived dynamic cast, base plus employee, and then get base salary.
What? Say it again.
Just write instead of derived pointer, dynamic cast.
Oh yeah, you could, but the trouble is this. The trouble is, what if that dynamic cast returns a null? Well, in that case, it wouldn't because you are inside it. Okay. You are saying that without using this, if you use this directly, the question is this: just try to dynamic cast everything to this base plus commission employee, and then arrow get plus. What happens if dynamic cast returns a null? In that case, you will have a crash during runtime. That's a bad thing.
But we check it instead here.
Well, yeah. Well, I mean, if you are checking it, then why don't you use it this way? Okay, good. Any questions? So let me. By the way, this is a type ID is a function. Let me. Okay, where is the type ID? Yeah, type info. If you include this header type info, there is a global function available named type ID. Okay, if you send your object to this type ID, it returns the type of your class, your object type. Okay, and you can print out its name. So C++ always knows the type names of your objects if you have the RTTI enabled. What is RTTI? RTTI enabled. You know it. I told you last time. Run type information, right? RTTI, run type information. If you enable this runtime type, which is by default is enabled, if you enable this run RTTI, your compiler knows the types of your classes, and it will print out the types of your classes that way. Okay. So by going back to these slides again. Okay. So upcasting is this way, downcasting. Upcasting is always possible. Upcasting is because we have this relationship available all the time. All the dog objects are pet objects. All the dogs in this world are pets, but not all pets are dogs, right? Some of them are different. All the commission plus employee objects are employee objects, right? But not all employee objects are commission employees. Okay, so you need to be careful about this downcasting. You could do that, but you need to make sure that you can make that conversion using the dynamic cast. Again, during the runtime, I make that decision. And I talked about this slicing problem. I did this before, and slicing problem, I talked about it. We talked about virtual destructors before, and casting again. Upcasting is always okay, but for downcasting, I do this. If I do the ppat downcasted to dog, if ppat is really pointing to a dog object, it is done. And this is not correct. The book says downcasting really done due to pitfalls. No, downcasting is done very, very often, and it is done for a purpose. And if you need to do it, just do it. Remember our Windows code that shuts down our computer? I have a Windows application pointer vector. When I am shutting down the computer, I need to close all the applications. See, what does this do? Can you tell me what does this do? It closes everything, right? It closes everything other than what? Windows Explorer, right? This says that all the pointers of my application, trying to dynamic cast them to Windows Explorer, okay? No, it does. If Windows Explorer is null PTR, yeah, it closes everything other than the Windows Explorers, right? If I can do this dynamic casting, in this case, that means that P points to a Windows Explorer. If it is null pointer, then I couldn't do that dynamic casting, then close it. So I am writing some specific code. This is general code, but this part is specific to Windows Explorer. What? Okay. So I don't like what book says about the downcasting, it is dangerous, or multiple inheritance is dangerous. those are not true. If you are careful, if you know what you are doing, those are very useful stuff, and you should not avoid using them. Downcasting or multiple inheritance. You learn about them and use whatever is available from the language. Okay, good. Any questions so far? Did Erdoğan Hoca talk about virtual destructors? Did he talk about it? I mean, if he didn't talk about it, they are not that difficult to understand. The virtual destructor means that if I have a, see, if I remember our hierarchy, partially filled array, I have partial filled array D. Let's say I have a pointer for a partial array, partial filled array double object, and I am pointing to a new partially filled array D backup object. Okay, let's say its size is 10. I can do that, right? Well, then these are, you may say that these are two different classes. Yeah, that's true, but there is a relationship. I know that all the partially filled array D backup objects are partially filled array D objects because there is a relationship. And I did whatever I want, then I did this. I am just deleting this P. When I say delete P, okay, when I say delete P, it will call the destructor of the partially filled array D class. But I know that P points to a partially filled array D backup object. So it is calling the wrong destructor. So to prevent these kind of errors, we always declare our base class destructors as virtual. Okay? Our base class destructors should be virtual partially filled array D. Okay? So our base class destructors are always should be they always should be declared as virtual. That's what we said. I think Erdoğan Hoca talked about this. I'm just repeating it. Good. Otherwise, as I said, it's going to call the wrong destructor of the base class. But I know that it's a right class object. That will cause some memory leaks for this case. Good. Any questions? Okay, if there are no questions, tomorrow we will continue with our next chapter, which will be, I guess, templates. So read the inheritance and polymorphism from the book, and try to implement that whole employee hierarchy yourself, and try to write that dynamic cast example yourself too, without looking at anywhere. And you will see whatever you remember, whatever you don't remember. That will be a good exercise. Okay, see you tomorrow then.